Oh, this is Mr. Pruitt. Today we're going to be talking about SI units and scientific notation. Now, before I get started, I want to talk to you real quick about why you need to learn this, because one of the questions that I get asked a lot is, well, we're Americans. We don't use this. We don't use this system, and why should we have to learn this? Nobody else uses it. Well, actually, there's the big fallacy. Everybody else uses it. In fact, we're one of only three countries in the entire world that doesn't use uh, SI units. The other two are those big modernized economic powerhouses of Liberia and Burma. So by choosing to use whatever we want to use, we put ourselves on basically the same level as Liberia and Burma. All of our other trading partners, all of Europe, Russia, China, Japan, uh, South America, they all use SI units as their units of measurement. And it's actually been estimated that on an annual basis, on a yearly basis, that not converting to SI units is costing the United States about $30 billion a year in economic inefficiencies. Although, that's one reason why we should learn this, and maybe even why we should fully switch over
So,
to
what
it
are
as a
SI
country.
units? Well, SI stands for System International, or International System Units. And basically, what they are is they are internationally standardized sets of units of measurement. Now, these aren't recent things. A lot of people act like net metrication or SI units are something recent. They came around kind of in the 60s when everybody was still kind of spaced out and everything. No, actually, these units have been around since 1790. And the biggest reason why they started using these was because scientists and engineers were having problems keeping their units, being able to verify each other's experiments, and keeping their units to make projects come out the same way. In fact, in a more recent thing, in 1992, the United States, NASA, lost a Mars uh, explorer, $125 million project, because one engineering team used metric units and the other one used traditional units, uh, and it ended up crashing. Now, these are really simple measurements. You have to remember that in 1790 the literacy rate was about 20%, and so these are units that are based on really simple measurements that be made easily, and they're based on powers of 10. Uh, these are the same units that your parents or grandparents probably call metric unit. Now, the beginning of the metric system is what we call the base unit. And a base unit is basically any unit that's equal to 1 unit of whatever is being measured. So if we're talking about uh, measuring distance, it's actually 1 meter, which is not this one right here. It's this whole stick that goes all the way out that you can't see. If we're talking about the unit for volume, it is 1 liter, which is what it takes to fill this beaker up to this top line. And the base unit for mass is what we call the gram, and this is a picture of 1 gram of pure gold. Now, those are the three most commonly used base units: meters, liters, and grams: distance, volume, and mass. But there are other units out there. Like there is a unit for that we use commonly for data storage called a byte, and that is an SI unit for the amount of data that can be stored on some type of disk or object. There's another one that people are somewhat aware of called lumens, which is a unit for how bright a light is. Now, I told you this was easy. When we're going to name these measurements fairly easily, SI measurements are typically recorded as a number that we call the magnitude, a prefix that tells us what power of 10 we're talking about, and then the base unit to tell us whether we're talking about distance or grams, distance or mass or liters or whatever. All right, so uh, a good example of this would be, let's say that you go and you sign up for a 5K race. Well, you know that 5K means 5 kilometers. When we look at that, the magnitude of that number is 5. That's just its number. There's 5 kilometers there. The prefix that we're given is kilo, and kilo means 1,000. Okay, so what we know is that we have 5,000 of something, and then the base unit is meters. So we know that this race is actually 5,000 meters long. It's a 5,000 meter run. Now, if you need to know kind of what that is in our traditional units, that's about 2.6 miles. If we were to say a 10K race, that would be a 10,000 meter run, or about a 5-mile race. Now, you need to memorize the prefixes, and I've included them on your note sheet so that you don't have to write them down. But you do need to memorize these, the large prefixes giga, mega, kilo, hecta, and deca, and that you need to know that they're a billion, a million, 1,000, 110, and you also need to know their power of 10. So giga is times 10 to the ninth, or kilo is times 10 to the third. Now, you do need to know that except in very certain and specific situations, it's not customary to use hecto or deca. Those measurements are normally made in terms of the base unit. So let's say that you get somebody says, "Oh, I have 1.5 decagrams." Most of the time, they're just going to say 15 grams. There's also a set of small prefixes that you need to know. These are prefixes that are between 1 and 0. All of these are larger than 0, but they all approach them. Those prefixes you need to memorize are deci, centi, milli, micro, and nano. You need to memorize its decimal number and its power of 10. Also, again, except in certain situations, it's not customary to use the prefix deci. About the only place that you see that is in medical journals where they're talking about uh, blood volumes or fluid volumes, or you know, maybe amounts of a drug, deciliters. Uh, but generally, we're it's not used. So if somebody said they had 2 decimeters, most of the time it's going to be reported as either 2/10 of a meter, 20 centimeters, or 200 millimeters, using a more customary unit. All right, so that brings us to scientific notation. You need to know that we'll be using scientific notation a lot in the class. And scientific notation is just a system for reporting very large and very small numbers. Now, the reason we use this is because it makes calculations easier, and it makes them more reliable. And there's another lesson after this that you're going to see in Blend Space that has um, that shows you how to make the calculations with scientific notation. For now, I just want you to know that scientific notation has a particular format. Okay, and the standard format is a digit followed by a decimal and then some other numbers. And usually those other numbers are determined by what we call significance. And normally it's not more than 2 or 3 other numbers. And then that's going to be multiplied by some power of 10. So to give you an example, we take this number here, 135 billion, and we're going to move the decimal over behind the 1 so that there's one digit. So here's our 1 digit. Here's our decimal. Afterwards, we have 2 significant digits, the 3 and the 5, and so we're going to put 1.35, and then uh, we've got this power of 10, 10 to the 11th. And how did I arrive at 11? Well, that's really pretty easy. What I did was I started where the decimal is right now, which is behind this last 0. And all I did was I just moved it over until it was behind the 1. So I counted over. This is 1 place, 2 place, 3 places, 4 places, 5 places, 6 places, 7 places, 8 places, 9 places, 10 places, 11 places, and that's my power. So it's times 10 to the 11th when I move the decimal over behind the 1. Now, following this lesson, you need to log in, go back to BlendSpace, and look at the next lesson, which should show you a whiteboard, and I will have done some calculations and showed you how to do some things like multiplying and dividing and adding and subtracting with scientific notation numbers. I hope you've had a good day and learned something from this. Thank you, and bye.